All right, folks, welcome back to another episode of Math with Dr. Math. All right, so what we're analyzing here is we got a couple of equations to look at. Okay, so we said whenever we're not dealing with interest compounded continuously, we're looking at this particular formula. But when we do have interest that is compounded continuously, this is our go-to formula right here. All right, so let's look at this example here that you have in your notes. All right, so here's your scenario. Suppose that you have $8,000 and it's invested. All right, so we're investing $8,000 and it's paying about 4.5% per year under the following compounded options. All right, so our first case here is we're compounding this annually. So if it's annually, then we know that our n in this situation, because it's compounded annually, our n is going to be 1. All right, our second situation says that's compounded quarterly. So you could imagine n is 4, right? Because it's compounded 4 times per year, quarterly. Compounded monthly for number 3 here. Well, we could imagine again, n is 12. Compounded daily, all right, assuming we don't have any leap years or anything crazy going on. So this n is 365. And number 5, compounded continuously. All right, compounded continuously. N is what? Good. So if you heard the person in the back, what they said is, we do not use n in this case, right? Because we need to use this formula right here. Because here's our big, this is what we're looking for. Here's our hint right here. It says continuously. So underline continuously. All right. So we're actually using this formula right here. All right. So let's do a few examples. I'll just look at 2. All right. So let's look at number 3. All right, so number 3, this is what we have going on for problem number 3 here. So it's compounded monthly. All right, so I'm using this formula right here. So we have A equals P. So the amount that we invest is $8,000. So you have $8,000. All right, times 1 plus our rate. Our rate is 4.5, so we got 0.045. All right, and we're going to divide that by n, and in this case, our n is 12. And our exponent is n times t, so our n again is 12 times t, and notice at the bottom, we're saying determine the amount in the account after 5 years with each option. So we're going to multiply this by 5. So they're always going to tell you a time. All right, so we want to simplify this as much as possible before we actually plug this into our calculator. So we have 8,000 times 1 plus, and let me highlight this right here for you real quick. Let me choose a color to highlight this. I could actually simplify this piece, right? So let's go ahead and pull out our calculators, and we're going to divide 0.045 divided by 12. All right. What's going to happen, though, is you might end up with a long decimal. So if you want to be exact, go ahead and enter this entire thing into your calculator. Okay, and I'll show you how to do that. All right, but sometimes our decimal comes out nice. All right, so let's go ahead and do that. All right, so I plugged into my calculator, and you see that we end up with let me change my color here. We end up with 0.00375, and that's raised now to the 60th power because we went ahead and multiplied the 12 times that 5. All right, so this is what we have. So now let's go ahead and plug this into my calculator. But notice, when I plug this into my calculator here, I'm not going to actually plug in 1 plus 0.00375. I'm actually just going to add the 2. So the number I'll be entering here into my calculator will be 1.00375. So I could go ahead and just add that up. All right, so let's go ahead and use our calculator again, and let's see what we get. All right, so notice we went ahead and we plugged that in into my calculator, just as so. Let me zoom in here just so you could kind of see what I did, right? So again, make sure you're good users of those parentheses right here. All right, so make sure you use those parentheses. And so we have 8,000 times the quantity, 1.00375, and that's raised to the 60th power. All right, and as our output, that's what we got right there, 10,014. And let's go ahead and round this to the nearest cent if we're talking about, since we're talking about money here. All right, so our final answer here, I'm going to write this down. Ends up being $10,014 with 37 cents. All right, so that's problem number 3 for you. All right, so let's go ahead and look at this next example. I'm going to get rid of this right here. Let's see. All right, so that's example number 3. Let's go ahead and let's take a look at number 5. Let's see what happens when we're compounding this continuously. All right, so number 5. So again, make sure you understand which formula it is that you're using. So now we're up here using this formula. All right, so let's get to work. So for problem number 5, we're looking for that final amount if we start again with $8,000 invested. That's our P. E is our constant, right? We talked about that number, 2.718. And we're raising that to the power of R, which in this case is 4.5%. So we have 0.045. And you're going to multiply that times the number of years. And in this situation, we said that is 5 years. All right. So again, if you want to play it safe, what I would do is I would go ahead and simplify this first before you plug it into the calculator. And it just is going to help us, reduce the chance of errors. So we end up with 8,000 times E, and let's go ahead and multiply this in our calculators, and we end up with, all right, we end up with 0.225, I believe. If you could just go ahead and verify that. All right, good. I'm getting a wink in the back. Oh no, you got something in your eye? All right, someone else is confirming that. Good. So there is our product when we multiply that. All right, so let's go ahead and finish this off. So let's polish this off. Go ahead and plug this whole thing into your calculator. All right, so I'll do it with you. And it looks like we are getting 10,018 and 58 cents. All right. So again, just be very careful. Let me kind of zoom in here. So when you're plugging this in, notice how when I plugged it into the calculator, I have 8,000 times to activate my E on this calculator, I had to hit second right here. So let me kind of add some shapes just to make sure we're on the same page. So I used second, this button right here, and then I went ahead and, oops, I get that shape back. And then I hit this E right. Let me try that again. Little technical difficulties here. Let me get this another shot here. Let me change my color up. See if that helps out. Damn. But anyways, you kind of see the Ln button. Let me move that out of the way here. Screw it. You know where the E button is, right? All right. So that's what we're going to do there. All right. So this is our final answer. I'll give you a second to go ahead and copy that down before we look at this next problem. And I just realized I'm probably already giving all this to you, so there's probably nothing to copy down. So let's go ahead and look at the next problem. All right, so let's go ahead and look at an exponential function in a real world situation. All right, example 5 here. So we're looking at the half-life of radium. Okay, so we're going to look at the half-life of radium. And I believe, who was it? I think it was Mary Curie. It was almost 1900 for those of you studying chemistry. So I think it was like 1898 or 97. I think it was 98. But she discovered the highly radioactive element radium. All right, so this is what we're going to look at here. And I just remember that because, number one, she won the Nobel Peace Prize. But the real thing that got it embedded in my memory was because it didn't come without a price. She actually died much later from complications from being exposed to so much radiation. And I think she actually won 2 Nobel Peace Prizes. But let's take a look at this. So let's look at half-life here, all right? So we're going to look at the half-life of radium. All right, so she did much exploration in this field. All right, so the half-life of radium, of this particular radium, is 1,620 years. All right, so in a sample originally having 1 gram of radium 226, the amount of grams that we're going to denote as A of t present after t years is given by this formula right here. And t is going to describe the time in years after the start of the experiment. So what they're giving us here is they're giving us the amount of years after the experiment has started. And we're going to go ahead and if they give us the number of years after the number of years that have passed, we could go ahead and say, well, how much radium do we have if we started with 1 gram? All right, so let's look at our solutions here. So let's look at number 1. All right, so what we have here is the following. All right, so for number 1, here's the formula we're going to be using, just as we said before. All right, we're using that formula right there. And this time we know our value of t, right? So wherever we see t, we see that we're going to plug in 620. All right, so let's go ahead and plug that in. And what we end up with, all right, so forgot my microphone. We end up with the following, right? So we're going to go ahead and, as you see, we're going to plug in 1620 into our function. So wherever you see wherever you see t, you go ahead and enter 1620. Damn, what time is it? It's 1 a.m. No wonder I'm saying twee. All right. So we go ahead and enter in 1620. All right. And what's nice about this is our exponent becomes what? Great. It becomes 1. Now, if you forget that, just think of me, number 1. All right. So we go ahead and enter, do the math, and anything raised to the power of 1 is itself. So we end up with half here for our solution. And let's see if this makes sense. All right, let's go back and talk about this. So you started with 1 gram of radium. All right, so we started with 1 gram of radium. And it's told us that the half-life of this was 1,620 years. So what that means is after 1,620 years, whatever amount that you started with, you should end up with half of it. All right, so for part 1 here, look at that. We're saying 1620 years have passed. 1,620 years have passed. So we expect there to be only half of that gram left, right? Because after all, this was the half-life. So it makes sense for us to have half of that original gram. And that's exactly what we got. Perfect. So for examples 2 and 3, you could easily see all you'll be doing is sticking in these values of t into your function. And what that'll do is that'll tell you how much radium you have left after that period of time. Alright, so hopefully that makes sense. So what I want you to do right now is go ahead and plug in these values of 2 and 3 and go ahead and see what you get and then compare your answers with one another. Alright, so go ahead and take care of business there.